Hello. Hi, Karthik. Am I audible? Hello. Am I audible? I will wait for, yeah, Lalita.
Yeah, yes, sir, you're audible.
Okay, yeah, fine. I will wait for a few more minutes and then start.
Okay. These sessions don't have fixed timing, is it?
What do you mean by fixed
In
timing?
the sense because first few weeks the time was same, and yesterday I missed looking at the time. Mm, It was not every time. It was first 3 weeks at least. Every time it was 3 to 5 Saturday session, and
Okay. Now, on Sundays, the session is from 7 to 9.
okay, okay.
It has been from
And
7 to 9.
yesterday it was like 1 to 3. So it was almost over yesterday. I was every Saturday I was
Okay,
joining.
okay. Okay, okay. Hmm.
I missed looking at the time.
Okay, yeah. So you get a email notification
Yeah,
every
yeah, yeah.
week.
We got, yeah, yeah. In that it was written, but
Uh,
I just assumed that okay, every Saturday it's going to be same time.
okay. It's normally the same time, but yeah,
Sometimes.
sometimes it changes.
So your name?
Uh, What? My name? Yeah,
Yeah.
my name is Suchit Prabhu. I will wait for 2 more minutes and then start.
Okay.
Fine, let us start. Okay, so hi, I am Suchit Prabhu, PhD at IIT Delhi, working with Manik Verma and Sumit Agarwal on extreme classification. Okay, so the plan for today is we'll first revise whatever was covered this week, and then after that solve few questions, and then look at two applications of PCA and SVD. Uh, so one is yeah, we'll uh, do background removal, and the second task is topic modeling. We'll see how PCA is used in those applications, PCA and SVD. And then finally, if we have some more time left, then yeah, we'll try to code a logistic regression from scratch on a real world data set. Okay, so fine. So before we begin, yeah, so can you all introduce yourself to me? Let's start with Karthik. Karthik, yeah, so Lalita Raman. Am I audible? Hello?
Hello. Yeah.
Yeah.
There were two. Can you hear me, sir?
Yeah, I can hear you.
Yeah, yeah. I don't know why there were two team session got open.
Okay.
Hi. I'm Lalita.
Uh,
Um, I I'm currently just a learner. I was working. I'm a computer science engineer. I was working long ago. Uh,
okay.
it's a 15-year kind of break for me right now, and I just happened to start this something I started some courses I did on YouTube, and I just started liking this machine learning, and one by one I started doing some courses, and that's how I landed here, and I'm enjoying.
Yeah. Nice. Thank you.
I love math, and there was a lot of math that was actually interested me more.
Okay. Okay. Thank you. Yeah, Saurabh Jha. Okay, fine. So first, let us see what was covered. So, can anyone tell me? So, how many of y'all have gone through the videos for this week? And tell me what was covered.
So, eigen vectors started with eigenvectors, eigenvalue, eigenvectors, how to
Okay.
compute, and why it is required, and what is the use, and some theorems were there. And
Okay.
after that was using eigen vectors, this eigenvalue decomposition, and
Hmm.
lot of derivations were there. After a point, I mean, till a little bit I was following, and afterwards I was not able to follow much.
Okay.
And then came PCA,
Mm-hmm.
and an example was given. This variance and covariance, those concepts were also taken, and this PCA, and then some example was taken, and then at the end singular value decomposition.
Decomposition.
If it's a rectangular matrix, how do you go about uh,
Decomposing it.
yeah,
Yeah.
decomposing it? So I mean, initial, just when it starts, it's all okay. Finally,
Mm-hmm.
I just wrote down the formulas. Beyond that, I was not able to focus. But this book, in the first lecture, this one book, Goodfellow book, was suggested.
Yeah,
I
yeah.
have that book, and initially I was not able to follow much, and I was like skipping all the linear algebra, thinking that, oh, I already know, but um, I I don't know
Okay.
actually. I thought like
Uh,
superficial, yeah, yeah, these things I know, but this book was very useful after the lectures, when I around Thursday, Friday, and all, when I started looking at this book,
mm-hmm.
it was very good book. Was very useful. Little bit
Okay, okay.
when things were like derivation was not given, which was good, but mm, the concept wise, when they said it little differently. So when someone says little differently, you get a wider picture.
Mm-hmm.
So that was good. And then some concepts also, which have not done, so they have touched those concepts. If it was
Okay.
mentioned in some norm, this Frobenius norm was mentioned in the lecture, so some
Mm-hmm.
couple of norms are given in the book, so that way it was good. So that is a gist of the.
Okay. Okay, fine. So, for linear algebra, you can take a look at Gilbert's triangle. So, Gilbert's and lectures, and also there's a book by lecture Gilbert's triangle. So, which most of undergrad, yeah, uh, it's prescribed in the syllabus. So most of them solve questions
Okay,
from
okay.
that book. And also there
Uh,
are videos by three blue, one brown on
yeah,
linear
yeah,
algebra.
yeah, I
Those
know.
video lectures are also good.
Initially, I had done like from Khan Academy little bit, but when it was getting too much in, I mean, I've not like actually, my daughter is studying in IIT Delhi,
Okay,
so she told me that she's in third year,
okay, okay.
and she said that it's a textbook for her, the same Goodfellow one.
Mm-hmm.
She has almost every year she has machine learning, so they are doing so much in depth of the linear algebra, and that and all I've
Mm-hmm.
not done. So
Okay, so your daughter is in which department?
she is in this computational mechanics,
Mechanics. Okay.
comes under applied mechanics department.
Mm-hmm. Okay.
Yeah, so when you said you're from that, I was like, good to know.
Uh, uh,
I've been having very good experience with NPTEL, the TAs and the lecturer, I mean the professor who's taking the
mm-hmm.
really nice way of explaining, and thank you.
Okay. Yeah, so in the yeah, so this week we started with eigenvalues and eigenvector. Okay, and then saw few basics of linear algebra. Okay, saw eigen decomposition, and then yeah, principal component analysis and its interpretations. So there were three, I guess. So one so we derived the PCA. So one was through yeah, covariance between in the new dimension is minimized. Okay, and the second was we tried to maximize the variance of the projection of the data in the new subspace. And the third one, yeah, third one was to minimize the residuals after the projection. Okay, and also it ensures that data can be represented using less number of dimensions. And finally, we yeah saw singular value decomposition. Okay. Yeah, so here, yeah, so the two interpretations that we saw. So in the one, okay, the one interpretation, so what we did was So we try to minimize this. So in PCA, the task is given the data points. So these points are the data point. Okay. The task is to find a subspace, okay, such that when we project the data points onto this subspace, okay, uh, so one way to derive those vectors are through minimizing this residual. Okay, and the second one is to, so these are different interpretation how we arrive at the same thing. And second was to maximize this variance. So when we maximize, so we arrive at the same equations when we do these things. Okay, so this is just a revision of what we covered. Okay, let's go through the lecture notes as well. Yeah, so we started with eigenvalues, what eigenvalues are. Okay, its definition, Ax equal to lambda x. Then, yeah, we saw some theorems. Yeah. So dominant eigenvalue of A is whose absolute value is maximum. So that is the dominant eigenvalue. And then we looked at stochastic matrix, and dominant eigenvalue of stochastic matrix is 1. The proof is also given. You could have. So did anyone go through the proofs?
No.
Okay. Now it's fun to like go through all the proofs because you'll get a better understanding of what is happening. Okay, then yeah, so then vanishing, exploding, we'll look at this. Yeah, these all these concepts will be useful in the coming weeks, where when we look at RNNs and look at exploding and vanishing gradients. Okay, and then some basics of what yeah, independent basis vectors are.
So can you just go to that first slide of independent? This particular, yeah, this one.
Mm-hmm.
Uh, Somewhere when I was doing, I mean, I felt I could not understand. I said that it is like it's so very contradicting. Let me see if it is the same one. Basis is fine. Yeah, in this definition of linearly independent vectors, uh,
Okay,
set vectors
set
is linearly independent if no vector in the set can be expressed as a linear combination.
combination of other vectors.
Okay, now I got it. Somehow, like I understood now.
Uh,
Okay, fine.
yeah, so if we so take V1, V2, Vn as the column matrix, and create a matrix out of this such that these V1, V2 are columns. So then Ax equal to 0 just has one trivial solution. So that is
Hmm.
also a way to look at this. So then we looked at orthogonal basis and how eigenvectors of matrix. So yeah. So if a matrix A has distinct eigenvalues, then the eigenvectors are linearly independent. So the proof is also given here. Yeah, I encourage you to go through the proofs because yeah, the proofs are interesting. Then yeah. So we came to symmetric square symmetric matrix. So square symmetric matrices have real eigenvalues and the eigenvectors are orthogonal. And a symmetric positive semi-definite matrix has all positive eigenvectors. Uh, then we came to eigenvalue decomposition. So where a matrix A can be represented.
Also, just to interrupt this, time complexity calculating, are we supposed to know? Because couple of slides, servers are saying that the time complexity for this is n square, and so.
Okay, yeah, it's better if you know the. For that, you'll have to know how this inverse is computed.
Mm.
All that thing, yeah. Yeah, it's better if you know for that. And then for symmetric matrices, we saw key. It can be written as U epsilon U transpose. Fine. And then after that, we came to principal component analysis and how yeah, we are trying to project the data points into subspaces such that its variance is maximized. So using that as an objective function, yeah, so we found that the variance is maximized along the eigenvector with so the maximum variance is along the eigenvector with the largest eigenvalue. So went through the proof. And the three interpretations, and then finally, yeah, we looked at yeah, some of the applications of PCA. Then when we have square rectangle matrix, we looked at SVD. Okay. So performing, yeah. So doing PCA, so what we did was we took X transpose X, which is the covariance matrix, and then found eigenvectors and eigenvalues of that covariance matrix. And that is similar to finding SVD of just the X matrix that we have. So instead of, yeah, and the way we find SVD is we again compute X transpose F and do that eigenvalue decomposition. So that is the relation between uh, SVD and yeah, eigen decomposition. Fine. So now let us solve a few questions. Okay. So these questions I have taken from previous year. So I'll read out the question first, and then yeah, we'll together like come up with an answer to all these questions. How many? So I think there are 10 questions. Okay, let's start. Okay, so which of the following is a measure of amount of variance explained by a principal component in PCA? Covariance, correlation, mean absolute deviation, and eigenvalue. So what is the correct answer? Yeah, so it's eigen values, right? So maximum variance is along the eigenvector of X transpose X, which has the maximum eigenvalue. So based on that, we chose the new set of bases. So the amount of variance was measured using the eigenvalues. So the answer is eigenvalues. It's a direct answer. This just theoretical answer. Okay. Moving on to the next question. What is or other limitations of PCA? It is computationally less efficient than autoencoders. It can be it can only reduce the dimensionality of a data set by a fixed amount. It can only identify linear relationship in a data. It can be sensitive to outliers in data.
This autoencoders we're about to do, we've not done.
Okay.
There was a question in our quiz also, what is between which is something uh,
Yeah,
relating.
so autoencoders are also used to reduce the dimensionality like PCA. But there we use a neural network. So yeah, so you can think of it as uh, something you're doing PCA with neural networks, something similar to that. So so the first option is not is incorrect. Okay. Yeah, so using autoencoders, you can get the same eigenvectors via like performing the optimization. You can arrive at the same vectors, but it is not like more efficient than PCA. So what about
Second
the
is
second?
also incorrect. No, it's not fixed, right? I mean, you
Yeah,
can
yeah,
use.
yeah. Yeah, second one is also incorrect.
First
So what
is
about,
correct, only linear relationship in data.
yeah, so this is correct. It can only identify relationship. So what about the
Third is
fourth option?
also, it is sensitive to outliers is also correct.
Yeah, yeah. So C and D are correct.
Mm.
The other two options are wrong. Okay. Yeah. So moving on to third question. Which of the following is property of eigenvalues of a symmetric matrix? The eigenvalues are positive, eigenvalues are always negative, eigenvalues are real, eigenvalues can be complex number with imaginary part non-zero.
Real.
Yeah, real. So we'll look at the proof as well for this, the second part, third question. Okay. So if A is symmetric, so then A equal to A transpose. Okay. So then if we take conjugate of both the part, because A is a real symmetric matrix, so we'll get this A x bar equal to lambda bar x bar. So is this step clear? Okay. Now if we look at uh, yeah, x conjugate transpose ax. Okay, so we'll get lambda x square, and similarly x transpose ax conjugate will get lambda bar transpose ax. And since it's a symmetric matrix, these two terms should be equal. So then lambda should be equal to lambda bar. So that means the imaginary part is zero. So that's why the eigenvalues are real. So any questions regarding this proof? Yeah, so first we take the conjugate and then we use this property of symmetric matrix to finally arrive at this answer. Okay, let's move forward. Okay, so the eigenvalues of A are 3 and 4. Which of the following are the eigenvalues of A cube? Yeah, any thoughts on how to do this? Like, you don't have to be correct. There will be 3 cube and 4 cube. The answer is 27 and 64. So anyone wants to go ahead and like explain why the answer is 27 and 64? Okay, suppose yeah, x is eigenvector of A and its corresponding eigenvalue is lambda. Okay, so so let us see what happens when we multiply x with A cube. So a cube can be written as a square into A. So and we know ax is equal to lambda times x because x is lambda. X is eigenvector of A. So we can replace this with lambda x and continue this process and multiply x with A again, and then finally we'll get a a cube x is equal to lambda cube x. So lambda cube is the so x is the eigenvector of A cube as well, and then lambda cube is the new eigenvalue. So that's why the answer is we just have to take the cube of the eigenvalue of A. That's why we get 27 and 27 and 64. So is the answer clear or
Yeah,
okay?
understood.
Now if we have a 12 cross 12 matrix having entries from R, which is a real number, all entries are real numbers. How many linearly independent eigenvectors corresponding to real eigenvalues are possible for this matrix?
Well,
Yeah, so yeah. So how many yeah, so nothing is specified about the independence, right? Of the entry columns of the matrix A. And it's not necessary that given any random 12 cross 12 matrix, we'll get like suppose n cross n matrix will have n eigenvalues and eigenvectors. So 12 is possible if all the columns of the matrix are independent. Then, but we could
okay,
have
if
less
it
than
is
that as
not.
well, right? So it is 12, maximum that we can have is 12. And then 10 is also a possibility and 6 is also a possibility. So the answer is 12, 6 and
Okay,
10.
I need to pay attention to that.
Okay. The next question. Okay, so consider the following data points x1, x2, and x3. Okay, that's the following questions. So x1 is 2 comma 2, x2 is 1 comma 2, and x3 is 2 comma 2 1. So what is the mean of the given data point? x1, x2, x3. So what is the answer? You have to sum this and divide by 3.
1.67.
Yeah, 1.67. So
Yeah.
B is the correct answer. So fine. So so what is the covariance matrix? This is given by this equation, and x is the mean of the data points.
Wanted to ask, is there a shorter method? I knew only the x minus x 1 bar
So
into
so
x, and then the transpose of that
you'll have
multiplied.
to yeah
So there will be like three terms and little bit of calculation.
you'll have to do that, calculate
Yeah.
everything.
Okay.
Or what? You would also write code for it if you don't want to. Yeah. So let's use PyTorch and then create these three tensors and do the calculation. Two comma two.
For our exam, we will not be
Uh,
allowed to do this, right? We can't use
yeah,
a code, right? We'll have to use calculator.
yeah. So I've created these three tensors. I will first compute the mean. This is just x1, x2 plus x3 by 3. Okay, this should be 2 comma 1. So it's 1.6x. And then covariance is x1 minus mean times transpose. Divide everything by 3. Yeah, so the answer is A. So the answer to this question is A. Okay. Yeah, you just have to apply the formula and come with the answers. There is nothing much to think. Okay, so moving on. Yeah. The maximum eigenvalue of the coherence matrix C is. So which is of this matrix? So what is the maximum eigenvalue of this matrix?
This again we have to calculate only, right?
Yeah, yeah. So how will you calculate the eigenvalue for this matrix C?
P minus lambda I.
And then you'll compute the determinant and
Yeah,
equate that to
equal to
0.
A 0. Yes. I'm not calculating now. I'm not calculating
Okay.
because it is anyways it is of
Now,
decimal
because
and all.
this is symmetric matrix, the answer is if you try to calculate, it'll be very simple. Because yeah, you'll get it in a square minus b square form. So then it's easier to calculate lambda. You don't have to expand it and then collect all the terms. Okay, let's see what the answer is. Okay. Yeah. So we have to calculate determinant. So if we take this, so a minus lambda I x should be equal to 0. Okay. So that means So uh, so that because of this, so the determinant should be 0 because x is in the null space of this A minus lambda matrix. So columns of this matrix won't be independent. So that's why its determinant should be 0. So equating that to 0, we'll get this. And so we'll get this simple form, which is 0.22 minus lambda the whole square minus this. So which is a minus b, a square minus b square. So we can expand this as a plus b minus b. And lambda will be 0.33 and 0.11. So, so answer to this question is option A. So is this clear?
Yeah.
So yeah, the eigenvector corresponding to the maximum eigenvalue of the given matrix C is.
You again substitute for
Yeah, you substitute lambda and
lambda
yeah.
and equal to 0 vector.
Mm. So you then solve for Ax equal to 0 and
Yeah.
get x1, x2. So here I don't think you'll have to solve by just looking at the matrix that you get. You can directly like tell the eigenvector.
Sorry, I mean what you don't have to do?
Now, so this is a symmetric matrix, and the equations that you get. Uh, so after substituting lambda, the matrix that you get, uh, that is like you don't have to solve for x1 and x2. So just looking at the matrix and substituting some value of x1, x2, you will find out the answer. You don't have to do all the calculation. So what is the answer to this question? Anyone?
No, I'm not calculating, sir.
Okay.
I did this for the quiz question. I did this.
Okay. Yeah, so when you substitute lambda, so you'll get this. And you can see if you substitute 1 and 1,
Minus
uh,
1, 1. I mean, if you give me the directly after
yeah, yeah,
calculating this, then minus 1, 1.
minus 1, 1, yeah. So, so the answer should be
The third one.
the third one, also the second one.
Why second?
So if
Can you
you take
do that
0.71
again?
outside, here
Can you
also you'll
show
get
me
1
the
minus 1.
calculation? Point.
Think of it like this. If you take 0.7 on outside, you'll get 1 minus 1 1 again, right?
Yeah.
Yeah, so
So both are,
both are correct.
but this is not a multiple correct answer.
Yeah. Yeah, it's not, but both are correct for this case.
Okay.
There could be some mistake in the
Okay.
question, but yeah, both are correct.
Okay.
So what is the determinant? So it's clear, right, why both are correct?
Yeah.
Because
Yeah.
yeah. What is the determinant of 2 cross 2 matrix that has eigenvalues 4 and 5?
20.
Yeah. So why is the 20? Why is 20 is the answer?
I know the formula.
Huh?
I just know the formula.
Okay, you just multiply these two eigenvalues. Okay. Let's see eh, why the determinant is product of the eigenvalues. So here is the proof for that. So if we take the small 2 cross 2 matrix with entries A, B, C, D, its determinant is AD minus BC. Okay. So suppose we try to find the eigen uh, values of this matrix. So we'll compute A minus determinant of 8 minus B and equate that to 0. Okay, so if we expand this, the quadratic equation that we get is lambda square minus A plus B lambda AD minus BC equal to 0. Okay, and yeah, so we know that product of two
Yeah. Quadratic
yeah, so
formula.
in quadratic equation the C by
Mm.
A is the
Mm.
product of the roots of the equation.
Yeah.
So from that, yeah, that's why the determinant is product of the eigenvalues.
Oh.
Okay. Yeah, so those are the questions. Okay, and then now let us look at applications of PCA. Okay, so two applications we'll look at. One is background removal. So what we'll do is we'll take a real world video, okay, and then try to remove background from it. We will separate the foreground and the background from the video. And the second one is topic modeling. Okay, so given a document, so given many documents, we'll try to look at what topics are present in that document. Okay. Fine. So we'll use PCA for background removal. So our goal is, so given image like this, Okay, we want to separate the background from the foreground. Okay, so the image of the street is present here, and the people that are walking on the street will become the foreground. Okay, so here, so how many of y'all know Python? Because I'll be using Python for all these examples. So can y'all raise your hand if you know Python? Okay, and two, I can see two hands. Okay, so yeah, so I have stored the video in this path. Okay, so if I look what is there in this path, so it threw this error because there is a space over here, so I'll have to put this colon. So now it will show. So there is this video, okay, in this video folder. Yeah, we'll load this video 003.avi. Okay, so for that I'm using this MoviePy library. Okay, and reading it as a video clip. So MVP, so this here I'm importing the MoviePy library over here and using this function to load the video. Okay, and this is how the video looks like. So I have clipped the video and yeah, only displayed the 50 seconds of the video. Because the total duration is 113. I will just look at the 50 seconds clip. So it's a street and people are moving. So the foreground would be all these people, and the background would be the street as well as the buildings. Okay. So how will any idea how will PCA or PCA principal component analysis would help us here? So what exactly does PCA? So what does it do, and how will it help us in this case?
No idea, sir.
No idea. Okay. So what exactly happens is we are trying to project the vector into a subspace such that maximum variance is like captured. So it captures all the important features, okay, and then removes the rest. So what do you think are important over here? So which is present in like most of the frames. So that is the background, right? And the people which are moving, it will not be present in all the frames. So 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 when we perform SVD or PCA, so what it'll do is uh, it'll just keep the, so when we approximate the matrix with the lower rank matrix, what we'll get is the background will remain and the foreground will get removed. Okay, so that is what we expect as major important feature which is present in all the frames other is the background. Okay, we'll see like why is that the case. Okay, so what we'll have to do now is So given this frame, so we'll have, so a video comprises of uh, images, right? So what we'll do is we'll take each frame from this image and then convert it into a vector. So for each type step, we'll have like one image, we'll stack all the images and look at the matrix that we get. So, so we'll not work with the entire image, we'll scale it down. Okay. So let's see how to get a frame from the image. So if you look at video, let's do get frame. And if we give a time step, it'll return a matrix like this. And to view it, we'll use matplotlib. So this is one frame from the image. Okay, so what we'll do is so an image has three channels. If we look at the tensor which is returned, or the NP array, okay. So we look, so there are, this is the height of the image, width of the image, and then there are three channels. So what first we'll do is we'll convert this three channel image into two channel image. So for that, what we'll do is we'll just take a weighted average of this last three uh, channels. Okay, and also, so when we convert this into a vector, that is, we'll just stack all the pixels in one column. So what we get is we'll get this many. So this would be the height of the vector, and yeah. So for faster processing, what we'll do is we'll scale it down. So we'll take 25%. Yeah. So each height and width we will yeah. So we'll scale it down by 25%. And the dimensions that we'll finally get is 60 cross 60 cross 80. So the height of the vector after this resizing, it'll just be 4800. So just 60 into 80. So this would be the height of each image. And then we'll stack all such images across different frames. And yeah, so for each second, I guess we'll have one. So we'll sample frames from this images, frame from this video, and for each of the image, we'll have like a column. So any doubts till now what we are doing? So we'll have to do some pre-processing before yeah, we can apply SVD on it and remove the background. So any questions or doubts till now? See what is happening in the code. Till now we have just read the video and we'll see how to convert it into a matrix now. So we'll convert video into matrix. Okay, so given this matrix, we will call this function RG2 gray. We're just multiplying it by a weighted average so that we get the grayscale image. So if you do that, this is what we get. You have to specify a CMAP over here. So by calling this gray function, it just averages the last dimension of the tensor, and yeah. So after that, we get a grayscale image which looks like this. So we'll do this for all the frames present in the video, and then reshape this resize this and yeah, flatten this out. Okay, so that yeah, and then concatenate all the flattened. So we have this array which is 340 countries, and to flatten it, we just use this flatten function. So we'll get a single vector out of it. So this is the shape after flattening. But before that, what we'll do is we'll resize the image so that we have a 60 cross 80 image, and then on that we'll perform PCA. So what we are doing here is we are just resizing. So first we are converting the image into a grayscale image over here. Okay. Uh, then resizing it and then flattening out into a vector. And we are stacking all such columns and forming a matrix on which we'll perform the principal component analysis. So is it clear what is happening in this function? Okay, so yeah, so we are converting the video now and all the images present in it into a matrix. And this is the output shape that we get. Okay. So each column in this matrix M is a frame from this video. And yeah, we can look at, so we can grab one column from this matrix M, reshape it and see like how it looks. So we are getting this blurry image over here because we have resized it as well before flattening it out. So we can look at other images as well. So each column in this matrix is a video frame, is a image in the, is a frame from the video. Again, this is how, so now if I plot the matrix M, so this is how the matrix M looks like. Okay. So in this matrix M, so the rows are pixel. So each column in this matrix represent a frame from this video. Okay. So each column is a this. So from different time step we have different images. We have stacked all those, flattened it out, and then stacked all the images. And this is what it looks like. Okay, so if you observe this matrix, you see it's fairly like uniform, but in middle you can see there are this lines, black lines, curvy lines. Okay, so what do you think these lines are? So these lines that we get are because of the people moving in it. So what happens is basically the background remains constant throughout different frames. Okay, and the small movements or changes that you see in this matrix when we create this by stacking all the images, the curves that you get here are because of the movement of the people. As people are moving, so these are the lines that we get. So is it clear what is happening in this image? So from this, it will be clear why performing SPD will remove the background. Yeah, any questions of what is happening in this? No questions? Fine. So what we'll do is we'll go ahead and perform like SVD over here on this image. And when we do a low rank approximation of this M matrix, what will happen is this lines that are there in the middle because of people moving, those lines will go away in the low rank approximation, because on we'll only retain the important features in that. So the low rank will have just the background, and then yeah. So when we subtract this image by it's a low rank approximation, yeah, we'll get the foreground as well. Okay, let's go ahead and see. So we'll be using sklearn for performing the decomposition. Okay, so yeah, so performing like eigenvalue decomposition on X transpose X is same as doing SVD on the triangular matrix X. So in our case, the matrix is not X, it's M. Okay, so we'll perform SVD directly on N, then yeah, computing X transpose X and the M transpose M and performing PCA on yeah, eigenvalue decomposition. So I've imported this SK library, and from that, yeah, use this randomized SVD just to get two components out of it. This is how, yeah, this is the shape that we get. So we have directly gotten the orthogonal vectors corresponding to the top two singular values. Okay. Okay. So can anyone tell me, so in SVD, this U and V are orthonormal matrices, right? So how do we verify it if it's orthonormal or not? So we have this matrix U. Okay. So how can we verify if it's orthonormal?
Dot product will be 0.
Yeah. So it's a matrix that we have now. So what can we do? Dot product should be 0. So okay. Yeah. So So what do you want me to do? So take a column like this. Ooh, sorry. Okay, so this is one column and this is the other column. Okay, you're saying ki the dot product, if we take the dot product, that should be 0.
Yes.
Okay. Yeah, let's do that and see. Yeah, so it's very close to 0. Fine. So is there, so this is, yeah, so is there any other way? Yeah. So what we could have done is, since it's a matrix, this U transpose would have done this. Okay, so what would be the dimension of this? And what should be the output of this? So we are doing U transpose U. So we are doing this matrix multiplication. What should be the output of this operation?
Identity.
Yeah, it should be identity matrix. So what we could do is, yeah, we could have just verified if this is close to 2 cross 2 identity matrix. So what NP close does is it's just take element wise difference. And then if it's within a tolerance, it will return true or else false. So if this U transpose U multiplication should be, so this is identity. So when we do this, this returns our identity function. We're just seeing if it's not close or not to that. And I think by default, the tolerance is 1e minus it. And when we did that multiplication, we were getting lower than that. So we were getting around, I think, 1e minus 18 or something. So this should return true. Yeah. Similarly, the rows of V are orthonormal. Okay, so what could be, so how to verify that if rows are orthonormal or not? So will it again be U transpose P or some other operation? So is this correct? So if we do V transpose V, should this be identity? So what is the dimension of V transpose? So V is over here, shape of V. Anyone?
So V is 2 by 11300. So 11300 by 2. We transpose. I mean, I can't see, it's too small.
Okay, it's smaller. Now can you see?
Yeah, 1 minute. One 11300 by 2 is V transpose.
Yeah, V transpose would be 11300, comma 2, right?
Yeah.
And what we want to verify is if the rows of V are orthonormal. So, so what modification do I have to do here to verify that? So here we did U transpose U, and that should be identity. Again we'll have to do some operation so that again we should be able to compare it with identity. What equivalent operation would it be for V? So size of V is this. This will return you, yeah, 11300 cross 11300 matrix. So that is not correct, right? So it should be V into V transpose. So now you'll get a 2 cross 2 matrix. This should be identity again. And this will verify that the rows are orthonormal in this case. Okay, let's see, this should again return true. And if you look at the shape, it'll again be 2 cross 2. I mean, yeah. So so now we have verified that, yeah, so U is orthonormal, has orthonormal columns. These are orthonormal known, and these are the singular values. Okay, so which gives us like importance of uh, each of those vectors. Okay, and we'll just retain. So we could have done SVD and gotten all the singular values, but that is much. So this is a faster implementation of that randomized SVD. So it's not an exact algorithm; it's a randomized algorithm, and it'll directly give us the vectors corresponding to the top two singular values of this matrix. Okay. Fine. So what we'll do is we'll use this approximation, which is low rank approximation, and we'll compute the entire matrix again. So, so what should be the shape? Okay, it's already given here. So the shape of low rank matrix is this. So can anyone tell me what is the difference between this matrix M and this the low rank approximation that we have gotten here? So what we have done is we have done SVD. So we have taken M, we have decomposed M into U, S, and V, U, S, and V, and then only taken the top two eigen singular values and thrown all the rest of the uh, vectors and the values, and then again constructed this matrix again using this low rank approximation. So should these two matrices be equal now, M and low rank approximation? So if we plot this low
No.
rank, yeah, it should not be, right?
Yeah.
So what do you expect? What will happen? So below I have plotted low rank again. Okay. So how will this? What do you expect will happen to this image? So this here I have plotted M. Okay, and here it's low rank approximation. So what will happen? What do you expect? How will the image change from here to the next image? So whatever important features are there, all those features would be present, and rest all will be removed. So we'll get a smoother version of it. So let me show you how the image looks like. So this is what we get. So this is the image M. This is not image. Yeah. So we have taken a video and then flattened out all the image frames present in it and constructed this M, and then applied SVD to this video, and this is what we get as the output. So similarly, as here each column represented an image, here also each column is a image in the video, but all the noise which was present here, all those noises have been removed, and only important uh, pixel, like important features of this image vector have been retained. Okay. So now if we so what we'll do is we'll take this low rank and yeah, look at one of the images present in it. So we'll grab a column from here and then yeah, resize it into the dimensions of the image, and you can see yeah, so here was, I think I displayed, okay, let's see image 140 here. So here you can see humans are walking in this image. So that makes the foreground of the image. Okay, and when we have done this decomposition, only important features are retained, and in the same image in the lower rank approximation you can see yeah, so people have been removed, so we just have the background now. So these curves which were present here, those were corresponding to the human movement of the human through the video, because we have stacked all the image, right? So the x-axis of this image corresponds to the time dimension. So as people are moving, so we'll get this curves over here, but after SVD, all those. So this is an application of SVD. We have just done SVD and we are able to remove the background from the image. And when we take the original image and subtract the low rank form of the image, we'll get the foreground. And yeah. So these are the humans which are present in the original image. So we have separated now the foreground and background, and by just using the singular value of decomposition. So this is an application of SVD. So is this clear? Okay. So here we saw, so we took two singular values. What we'll do is we'll see how this output changes when we just use one singular value. So what should be the shape of so let's see, the shape of M here is 480K cross 113K. Okay, 400,000. Okay, 4800 and 1300K. So what should be the dimension of U in this case? So if you have understood what is happening before, so you should be able to answer, yeah, what would be the shapes of each of this US and V vector. Anyone? So we are performing this randomized SVD and just keeping one singular value.
4800, 4800 should be U.
It's a matrix 4800 cross.
Cross 4800 only, no?
No, it's not.
No.
Okay, so we are doing SVD, right? So we are decomposing this M cross N matrix, okay, and constructing this M cross R cross R, and N cross R matrix. Okay, and R are the number of singular values, yeah, singular values. And what we have done is we have just computing the top singular value, only retaining that. So what should be the shape of U then?
1.
Yeah, it is. It should be 1. What about S?
S, 1 minute, S will be 1 cross.
Yeah, it'll be 1 cross 1. Because R, it's the same thing that we are doing here. We have fixed R to 1. Okay, we are just retaining the first singular value and dropping everything else. Okay, so this would be 1 cross 1 and V would be 1 cross 113. So if we look at the shape, this is what we get. So so now to get the low rank approximation, we'll just multiply everything out so that we reconstruct the matrix again using only the top singular value. Okay, so that will be an approximation to matrix N. So here what we are doing is we are just retaining the important features which were present in the matrix. So you can think of this like that. Now the shape of S is just 1, right? So what this does is it gives a matrix with values present in S as diagonal so that we can perform the matrix operation. Okay, so what would be the shape of lower rank then after this operation? So what should be the shape of this? It will be same as M, right? Because we are reconstructing M again using only the top one singular value. So we have this big giant matrix. Okay, we know that all the so so n is the dimension here. So you can think M as data points, M as number of features. Okay, so normally when we have like a very large, suppose M is very large, we there's an assumption that this data point lies in some lower subspace, and there are redundant feature present in it. Okay, so to identify, uh, so to project these these vectors into a lower subspace, okay, we come up with this decomposition, and in the lecture it was proved that retaining only the top singular values, yeah, so we'll have maximum variance in the projected. So when we project the data, so we'll have the maximum variance in the projected data when we just retain the top few values. So that is what we are doing here. So so from yeah. So so basically in machine learning, if we are using this, we would have just used U as the new features, right? And then instead of using M data points with n with feature dimension, we would have used this M data point with R number of features. But since because uh, we are doing background removal here, so what we'll do is we'll remove out and then again reconstruct the matrix so that the foreground is removed, and whatever is important is actually the background because it's consistent across all the images. So after again reconstructing, we'll get the background, and then subtracting by the original, we'll get the foreground. So this is like one more application. Uh, uh, so we got this, and yeah, so if we look at the, so we can do similar analysis. So we'll pick take a column from it and then yeah display it. So you can see just retaining the just taking just the top one singular value. This is also doing a very good job of removing all the uh, foreground. So we are getting background here. Similarly, if we yeah. So we are getting foreground as well. So yeah, so we have just taken the rank one approximation, and that is also doing a very good job in this case of separating the background from the foreground. Okay, okay, so these are two different examples. Yeah, so there are three people over here, and you can see it has removed. Yeah, I separated out foreground and background. So this was we had just performed normal uh, SVD, and then again reconstructed, and from that we were able to separate the foreground and background. But there are other algorithms as well which do a much better job than this. You can see there are certain artifacts in the foreground here. Okay, so there are white patches and all. Okay, so there is one algorithm called robust PCA through via primary component pursuit. Okay, so where the optimization, so instead of coming up with 3 matrices, so the objective here is to decompose the matrix M into two matrices L and S, where L is a row rank approximation of M and S is a sparse matrix. And this is what the minimization objective is. Okay. So to induce sparsity, yeah, we'll take yeah, this one norm of S matrix, and this is called nuclear norm of L. So nuclear norm is just tries to minimize the eigenvalues. So we'll not go through the details of this. We'll just see how. So it's an iterative algorithm. I'll share the code with you. You can go through it. I'll also share the paper if you want to read through this method. Okay. We'll just see how the output is. Okay. It's a much complex. It's not that complex, but yeah, it's more fancier than just performing SVD that we did. Okay. And this, yeah, does a much better job than what we saw before. Yeah, so here I have plotted all three images. The original image, the background and the foreground. Foreground and the background. Yeah, so in this helper function, if you give it a list of columns, it will display all the images corresponding to, yeah, those columns. And you can see these results are much better than the before ones. Okay, so any questions? So we saw one application of PCA for background removal. So any questions, or should I move on? So after this, we'll see one more applications
सर
of
आप ये
topic modeling.
फाइल
हाँ
शेयर करेंगे फाइल शेयर करेंगे आप
हाँ हाँ हाँ, फाइल शेयर करूँगा. So वो गूगल ड्राइव
हाँ
में
yes
yeah, I'll
sir.
share all the notebooks
Yes sir.
as well as the slides. Yeah.
Oh, okay thank you sir.
If you have to apply PCA on speech signal context instead of image, if you have to apply, let's say, speech with noise signal,
हाँ
then would it be, I mean, the noise signature, if it is the white noise, which is remain constant in terms of the mean across the frames, then it will be identified as
हाँ
the low variance dimension.
yeah. So you can do that as well. Yeah. So that is also an application. So it's just like background removal, right? Removing noise from yeah, an audio file. Yeah, so PCA could be applied. There could be other sophisticated algorithms as well, which do much better. But you can try out SVD as a baseline. Yeah, so the same algorithm can be used for that as well. Yeah.
Okay, okay.
So the noise would be, you can think of noise as the foreground and the actual audio as background.
Okay. So the limitation would be it will well work for white noise, not for other variable non-stationary noises. Is it, or
Now
what would be the
we'll have to try and see how it performs. I have not
okay,
worked
yeah.
on it, so yeah.
Okay, okay.
So
I
if
will
you
read.
want, in the next class, I can like see how it performs and let you know. So yeah, we can do that in the next class. If you want
Okay, sure.
me to do that. So we'll
Yeah, I
download
will.
some image.
Yeah.
Yeah,
Okay,
so
I
you
will
can
also.
use this. Yeah. So you can use the notebook, and then yeah, I think the MoviePy library also supports audio files, so code won't be that different. Yeah, so it'll be similar to this. Instead of movie clip, I think we'll have to use audio file clip, and the procedure
Mhm.
would be same. You can see how this performs normal SVD and the robust PCA that yeah. So you could try out this as well. Yeah, so where it directly decomposes into these two components, low rank component and the sparse component. So the sparse component will have all the noise, and yeah, if we take, for example, the audio case, and we'll have to see how different noise behave for this. Like there's no assumption what should be the distribution of the noise. So we'll have to try out and see how this algorithm behaves for that case. Yeah. Yeah, but yeah, it would be interesting to see how this behaves. Yeah. So I'll make a note of it, and yeah, we'll do that in the next lecture. Cool. Okay, fine. Moving on. Uh, so the second thing that we'll do is we'll do topic modeling. Okay. So given like a set of documents, our task is to find what topics are present in it. Okay. So yeah. So what we'll do is, given documents, we'll come up with this document term representation of the documents. So what basically we are doing is we'll list out all the words which are present in the entire corpus, and then this is just a co-occurrence matrix of how many times a given word occurs for a given document. Okay. And to do topic modeling, we'll again use the SVD. So we'll try out two algorithms. Okay, one is SVD, where we directly come up with this factorization, and then the second one we'll try out is non-negative matrix factorization. Okay, so we'll try out these two factorization. So the second one where we factorize this matrix into two matrices W and C. Okay, so here we'll use gradient descent and see how we can come up with these factors. Okay, so here this is like linear algebra way of doing things, and here we'll use a stochastic gradient descent and factorize the matrix. Okay, so we'll look at these two, how we can use this to come with topics for a given document. So for this example, I've taken this news group data set which is present in SQL. Okay, and we'll just yeah. So news group is a discussion forum. Okay, so this data set it's a collection of posts which the user posted, and for each post a category like a topic is mentioned. We'll only look at like these four documents from posts from these four uh, topics, which is atheism, religion, graphics, and space, and we'll see the topics that we get using SVD, are they similar to these four concepts? Okay, yeah. So we just have to call this function and yeah, specify we want the train subset and categories that we want. Okay, yeah, we'll just work with the body of the text and remove header, footers, and quotes present in the text. Okay, so yeah, so after this we have train and test data set. Okay, so formatting all this data set, it's already done in the sklearn library. Yes. So So in these 4 categories, we have a total of 200K data points. Okay. Now, so I've displayed your 3. So okay, let me. This operation is not clear here, so let me print out the number as well, serial number. Yeah, so this is the first post that we have from the data set. Okay, so this, if you can see, I have noticed that if you only have saved, so this is related to computer graphics. Okay, so which is one of the topics. See, and then if you look at the final one, figure seems unlikely to actually be anything but like a Perigeo. I think this is related to space. Okay, so yeah. So this is how the data set looks like. Okay, so we have this text and there is a category corresponding to each of the text. Okay, so we have just consider for this, and what we'll do is we'll uh, will take all this text and convert and create this term document matrix. Okay, so for that, yeah. So to look at the target values, we just have to, so there's one more attribute in this news group. So if you look at this news group, so it's an object. So it has displayed like a dictionary, but if you look at the type of this, it's a sklearn bunch. It's from this class. Okay, and it has an attribute called target names. Okay, so the data will have the text. So these are the classes present in it, and yeah. So if you look at data, this will have all the text present, which we saw previously. Okay, and the targets will have the class of each of the document. Okay, it's in this format. So I think 0 is for atheism, 1 corresponds to religion. Similarly, it has been okay. So those are the classes. Now to get actual text, class text, we'll have to like take this and index it using this target names. Okay, so this is what we like specified key what we want. Okay, so when we do this, so we'll see that the top 3 documents that we displayed. Okay, so first one was from graphics. Okay, because it was talking about some 3D stuff. Okay, 3ds file and all. The second one is related to religion, and the last one is something to do with space. Okay, so yeah, so what we'll do is we'll uh, take all this text, okay, split it based on the space present between them, and then create a vocabulary for each of the words. And then, so for creating this, doing this, counting this all the words, we'll use a sklearn feature extract, okay, and then create this vectorizer. So if you do this vectorizer.fit, it'll create that for each document, whatever word is present, it'll get that count for us. Okay, so what we have after this is this 2k cross 26k vector. So so we had 200 documents, and these are number of distinct words which were present in it after removing the stop words in the document, in the data set. And now this is how we'll get the vocabulary. So is it clear what is present in this vector? If you look at the shape of the vector, it's so this is how the matrix look like. So each row here corresponds to one of the documents, and the column signifies words. Okay, and it's just a coherence matrix. So if suppose a word was present in a document, the number of times the word occurred in the document would be present in this entry, vectors ij. Is this clear what this signifies? It's just we are counting what all words are present in a document and forming this vector. So is this step clear key what we're doing? So now to get the topics present in it, what we'll do is
Sir, these four categories are given in the data set, or we have decided that these four categories, graphics and we
now this we have
talk
we have
religions.
specified.
Yes, sir.
So there are I think there
We
are
have.
more topics than this. There are around 20 something topics. Yeah, this we have picked, and we'll see that after doing so when we model the topics of documents, okay, we'll see that we'll recover all these topics again from that topic model.
So after the studying the data, we have decided that these four categories can be the data
Now
can
you
be
could
divided in these four categories.
now just to yeah, visualize, we have picked this category topics. Now we could have used all the topics as well. Yeah. So for currently I picked just these four, so that it's easier to visualize what is happening.
Okay, okay, sir.
And so I've created this document term matrix. Okay, and yeah, so in this entire corpus of 200k documents, there are 26k different words. Okay, so let us see what words are present. Okay, so that we call as vocabulary of this corpus, all the unique words which are present. Okay, so it has all the words. So cosmos and all. So these words are, so this is related to space. So it has all these words. Okay. So what we'll do is to model the topics. Okay. Yeah, we'll do this decomposition. Okay. So the R dimension. So M is number of documents, and N here is the words present in the documents. So when we decompose this into this matrix, what we see is the R dimension will model the topics which are present in the corpus. And to get an idea what topics it is related to, we'll look at the words. So that is how we'll see what different topics it's modeling. So the R dimension would be number of topics, and to get what topic is being modeled, we'll look at all the words which are present in that given topic. Okay. So yeah, so I've just called this lineage.svd and passing this document term matrix. Okay. Yeah, this will take some time because we are not using that randomized SVD that we used in background removal. So it's doing the full SVD here. So it'll be a little slower. And this is what we get as output. Okay. So again, here also, yeah. So we can verify if this is orthonormal or not. It's the same operation that we did. U transpose. Yeah. So the vectors that we get are orthonormal over here again. Now let us plot the singular values that we get after this decomposition. Okay. Yeah. So this is how the plot looks like. Okay. So yeah. So first few values are very high and then it drops down very drastically. So let's see what happens when we just pick top 20. Yeah, so this is how the values decrease, singular value. Okay. So after this decomposition, okay, so the R dimension that we get model the topics which are present in the document. Now to see what topics are modeled, we'll just look at the words which are active for those topics. Okay, so I've written a function here which does that. Okay. Now we'll just consider top 8 singular values and see what topics are like, what topics these 8 model, singular values model. And yeah. So these are the topics. Okay, you can see the second one is about graphics. Okay, fourth one is a mix of atheism. It's also about religion. This graphic also. Okay, so yeah, so the last one is about space. You can see, yeah. So the topic. So what we started with. So we were able to recover it, and we didn't do any supervised learning over here. So everything was unsupervised. Okay, we just uh, took the document term matrix and computed this SVD and were able to yeah, model the topics which were present in the document. So yeah, nowhere was the labels were used to come with these topics. Okay. Now similarly, we'll do this topic modeling using yeah non-negative matrix factorization. Okay, so here we saw key in one shot we got this uh, through linear algebra. Now we'll use HDD to come up with these factors. Okay, so this is one more factorization method. Okay, so what I've done here, instead of just taking the frequency of each word, I have computed TF-IDF. So which is a way of normalizing the counts which are present here. Okay, so TF means term frequency. So instead of just count, we are looking at the frequency and then normalizing it based on uh, frequency of that given word in different documents. So if a word occurs like in lots of documents, that means that word is not important. So we'll have to somehow discount, like normalize that effect. So yeah. So so the matrix that we get after this is the normalized matrix. So we look at this. Yeah. So we'll use this and then yeah, come with the factor W in it. So the goal here is yeah. So given this vectors TF, IDF, we want to decompose it into WNH matrices. Okay. So W and H are like the parameters. So when we did linear regression last time, similarly we learn W and H from scratch here and come with this factorization. Okay, so let us create tensors for it. Okay. So N and M are number of documents and number of features in the matrix M, the original matrix. Okay, so we'll call the original matrix as M. Okay. So we will create a tensor using this. Okay, so yeah. And similar to previous one, okay, we'll just look at yeah, top 8 topics. That means after this decomposition, yeah. So after this decomposition, the features number of features is 8. So we'll keep it 8 for this case as well, for this decomposition as well. Okay, so yeah, so we'll randomly create this. Randomly initialize this to n comma n, and yeah, requires grad so that yeah we get, so because we are using SVD over here, we need the gradients, and we'll yeah, so we'll perform gradient descent and come up with this factorization method. So we, when we pass this, the PyTorch will keep track of the computational graph and give us the gradients with respect to the loss. So we specify this to no. So what suppose, so we have fixed this as D as 8, right? So the size of W would be m cross D. So what should be the size of H then, if you look at this equation? Okay. So in our case, this V is M, right? We want to decompose M into W cross H. So I have, yeah, initialized this to M cross D. What should be the shape of M H vector? It will be D cross N, right? Okay. So I want these entries of these matrices to be non-negative. Okay. And also want the standard deviation of this initializing to be a little smaller than the default 1. So what I'll do is I'll first normalize the data. And take the absolute value. Okay, so we have this matrix W, H, and also the target matrix M. Okay, so we have initialized W and H randomly, and yeah, let's see its shape. So M is the full matrix, W and H are its decomposition. Okay. So you can think of it as compression. So instead of saving all this, what we are doing is we are decomposing this into W and H. So So we'll require a lot less space to store all these values. So you can think of this as compression method also. Fine. So our goal is to reconstruct. So let us define a loss function here. So which takes in M, W, and H. And yeah. So we'll just compute MSE as a loss. Just square it and then mean of this. Okay. And directly use Adam from PyTorch. So we had seen Adam last time. Okay. And our parameters are W and H. Let us keep learning it as 1e minus 3. And betas, which we saw, which were the first and second moment, the Adam optimizer. Okay, and just create this for loop. Yeah, so you want to zero the gradients first. Okay, then compute this loss. Okay, so our goal is to we want this W and H to be a non-negative. Okay. So we want W and H to be non-negative, but we have not in the loss function we have not penalized uh, for this to be positive, right? So we'll see how we can modify this to penalize if W and H become positive. But for now, we'll just work with this MSE loss. Okay. So let's see what loss we get initially. So this is the loss initially. Yeah. Here you have to do loss dot backward so that we get all the gradients accumulated. Okay, and then optimum up step. I This is just to print our progress. Okay, let's print the loss. That will become better. Yeah. So yeah, so we could have done more modifications to the loss function so that these W and V are non-negative. But for now, yeah. So when we do this optimization, what we'll get is two factors. Okay, so earlier we had used principle from linear algebra to come with the answer in one shot for decomposition into this two orthogonal matrix and the singular values. But so we have taken another approach now for factorization. So we have initialized WNH from scratch and we are using gradient descent to come up with these factors. Okay, so this is called non-negative matrix factorization, but we have not handled the non-negative part here. We'll have to add like penalties to this for this to not be negative. Okay. So this will take some time. So we looked at, yeah. So it's already 9:06, yeah. We'll stop here. Okay, we'll continue from here again. So for this topic modeling, we saw how to do it with SVD, and we'll continue with this non-matrix factorization. Next class, we'll add two more terms to this loss function and then see what topics, compare the topics that this method comes up with the previous SVD method, and look at what are the differences between the two. Okay, we'll stop at this. Any questions? Yeah, I'll share the notebook. Yeah, so here I'll have to, yeah, I'll complete this notebook and then I'll share this. So any questions regarding this? So was this coding session like helpful, or do you want me to solve more questions? So I can do that. Okay. So we'll stop at, yeah, Lalita.
Yeah, this first example that you took, I was able to follow it to some extent because not much of coding done
Okay.
in real life. The second one was, yeah, it it became a little tough to. But it was
Okay.
good. The good part was to see how, because only the math is what I understood, or to some extent understood. But beyond
Mm-hmm.
math, this was good to see how uh, it was applied. Otherwise, it was for
Mm-hmm.
me, it was only the formula. Beyond that, I never understood or never tried to understand. So
Mm-hmm.
that way, that it was the first coding example was
Okay.
good to understand.
Yeah, so what I'll recommend is, uh, if you like, machine learning is mostly empirical these days. Okay, so you'll have to be a like very good practitioner to apply the algorithms. So yeah, so what I'll recommend is I'll share this notebook, and in the next class, before the next class, whatever example I go through, I'll share the notebook related to that. So you could go through the notebooks like before coming here, so you have an idea of what is happening. And yeah, also what you could do is run the cells along with me, so that yeah, it's better. You'll understand it better. Uh, yeah, so yeah, I recommend you go through all the notebooks. You don't have to understand what is happening in each cell of the notebook. You just run it once, see what the input output is, and yeah. So apply it to, so take the same notebook, pick up some other data set, okay, which is there on the web, and then try to apply it. And then during that process, like if you feel like you want to dig in deeper, you can see what is happening inside the code. Okay, yeah. They'll share this notebook. Yeah, anything else? Fine. So we'll end here then. Okay. Yeah. Thank you for attending.
Thank you, sir.